Which massive geological mysteries are scientists too afraid to publicly discuss? Story 1. The Great Unconformity is one of those things that doesn't sound that weird at first until you actually think about what it's saying. Because it's not just a missing layer here or there, it's literally hundreds of millions to nearly a billion years of Earth's history, just not there in the rocks. If you go to places like the Grand Canyon, you can actually see it with your own eyes, where very old basement rock sits directly underneath much younger layers with a clean boundary between them. Like someone just skipped a massive chunk of time and then started recording again. And the thing is, geology normally works like a slow archive. Layer builds on layer, sediment stacks over time, and you get this continuous timeline you can read. So when that timeline just disappears on a global scale, it raises a pretty big question. What removed all of that rock? Because it's not just that it wasn't deposited. In many cases, it looks like it was there and then got erased. One of the main explanations people look at is massive erosion tied to events like Snowball Earth, where huge ice sheets could have covered much of the planet and slowly ground down entire layers over millions of years, basically sanding away the geological record. Another idea is long-term tectonic activity where continents were uplifted and exposed, giving wind and water enough time to strip away enormous amounts of material before new layers formed on top. So, it's not like there's no explanation at all. There are a few that make sense individually, but none of them fully explain why this shows up so consistently across different parts of the world, or why the timing lines up the way it does. And that's kind of what makes it interesting. Not in a conspiracy way, but in a, this is a massive missing piece of the story, and we're still trying to figure out exactly what happened way. Because when you realize the Earth's history isn't a complete record, and that entire chapters can just be wiped out, it makes everything we do know feel a bit more provisional. Like we're reconstructing a timeline where some of the biggest events might have left almost no trace at all. Story 2. The Earth's core is one of those things we talk about like it's fully understood, but in reality almost everything we know about it comes from indirect evidence, which makes the details a lot less certain than people assume. We can't drill anywhere near it, so the main way we study it is by looking at how seismic waves from earthquakes travel through the planet, since different materials change the speed and direction of those waves, giving us a kind of rough internal map. That's how we figured out the basic structure, a liquid outer core and a solid inner core, mostly made of iron and nickel, and for a long time that was treated as a pretty clean and stable model. But the more precise the data got, the more complicated things started to look. One of the biggest surprises is that the inner core doesn't seem to rotate in perfect sync with the rest of the Earth, and some studies suggest it may even slow down or reverse direction over long periods, which is still debated but definitely not what you'd expect from something that deep. There's also evidence that the inner core isn't uniform, with seismic waves behaving differently depending on direction, suggesting internal structure or even layers within it. And since the core drives Earth's magnetic field, any unexpected behavior down there could have real consequences over time. So it's not a mystery we're ignoring, it's one we're still figuring out. Story 3. The boring billion is one of those names that sounds almost like a joke until you realize it describes nearly a billion years of Earth's history, where not much seems to have happened, at least compared to everything before and after it. Roughly between about 1.8 billion and 800 million years ago, the geological record suggests a long stretch of relative stability, with fewer major tectonic shifts, less dramatic climate change, and a noticeable slowdown in biological innovation compared to the bursts of activity that came later. When you look at the layers from that time, there's a kind of uniformity to them, fewer signs of massive upheaval, fewer major transitions, almost like the planet just settled into a steady state and stayed there. And that's what makes it weird, because Earth isn't usually quiet for that long. Before that period, you had major changes in atmosphere and early life. And after it, you get things like Snowball Earth events, and eventually the explosion of complex life. So this long middle stretch stands out. One idea is that nutrient levels in the oceans were relatively low, especially things like phosphorus, which may have limited biological growth and kept ecosystems simple for a very long time. Another is that tectonic activity may have been slower or less disruptive, reducing the kinds of environmental pressures that tend to drive rapid change. So it's not that nothing happened. It's that everything happened slowly, but the unsettling part is how long that lasted. Nearly a billion years of relative calm in a system that usually doesn't stay calm for very long, which raises the question of whether we're missing something subtle, or if Earth really can just sit in a kind of low-activity equilibrium for that long without anything dramatic breaking it. Story 4. The mantle plume idea sounds pretty straightforward on paper, like columns of hot material rising from deep inside the Earth, punching up through the crust and creating things like volcanic hotspots. But once you actually try to pin down how they form and behave beneath continents, things get a lot less clear. Under the oceans, mantle plumes are easier to visualize because you get relatively clean chains of volcanic islands, like a trail showing where the plate moved over a stationary source of heat. But under continents, the picture gets messy fast. The crust is thicker, more complex, and interacts with the mantle in ways that distort or mask what's happening below. So instead of a neat plume rising straight up, you might get something that spreads out, stalls, or takes on irregular shapes that don't match the classic model. Seismic imaging, which is basically our only way of seeing down there, shows structures that look plume-like in some places, but in others it's ambiguous, with hot regions that don't clearly connect to deep sources, or seem to originate much higher up than expected. That raises a bigger question. Are all plumes really coming from the same deep boundary near the core? Or are some of them forming through completely different processes within the mantle itself? There are ideas involving chemical differences, leftover ancient material, or even large-scale circulation patterns that create plume-like features without a single deep origin. And because this is happening thousands of kilometers below us, we're piecing it together from indirect signals that can be interpreted in multiple ways. So it's not that scientists are avoiding the topic. It's that the deeper you go, the less clean the model becomes, and the more it looks like what we call mantle plumes might actually be several different processes that just happen to produce similar surface effects. Story 5. The plate tectonic system feels so fundamental to how Earth works that it's easy to assume it's always been there, just running in the background since the planet formed. But one of the biggest open questions is why it started at all. Because early Earth wasn't just a slightly hotter version of today. It was a much more chaotic place, with higher internal heat, more frequent impacts, and a crust that may have been too soft or too stagnant to break into the rigid plates we see now. So the modern system, where plates move, collide, subduct, and recycle material, had to begin at some point, and that transition isn't fully understood. One idea is that as the planet gradually cooled, the outer layer became rigid enough to fracture into plates, while the hotter mantle below kept moving, creating the forces needed to push and pull those plates around. Another possibility is that early subduction events, where one section of crust begins to sink beneath another, may have acted as a kind of trigger, because once that process starts, it can become self-sustaining and drive the whole system forward. There are also suggestions that massive impacts in Earth's early history could have weakened or broken the crust in ways that helped kickstart large-scale movement. But none of these explanations fully pin down the moment or mechanism. And that's what makes it interesting. Because plate tectonics isn't just a feature of Earth, it's a defining one, shaping continents, oceans, climate, and even the conditions for life. Yet we're still not entirely sure how the planet transitioned from whatever came before into the dynamic system we see today. So it's not a hidden mystery, it's just one of those foundational questions where the evidence is incomplete and the origin story is still being pieced together. Story 6. The idea of lost continents sounds like pure myth at first, like something out of Atlantis stories. But there are actually real pieces of ancient crust buried deep beneath modern continents that don't match the geology around them. And figuring out what they are and how they got there is still kind of an open puzzle. Geologists call these fragments cratons or microcontinents, and some of them are incredibly old, far older than the surrounding land, which suggests they formed somewhere else and were later stitched onto larger landmasses over billions of years through tectonic processes. A good example is Zealandia, which is almost entirely underwater today, but still considered a continent because of its structure and composition, showing that continents don't always look the way we expect them to. But what's more interesting is what's hidden under existing continents. Seismic imaging has revealed regions deep below places like North America, Africa, and Asia that appear to be remnants of ancient plates or crust that got pushed down, broken apart, and buried during collisions long ago. These aren't neat, intact landmasses. They're distorted, partially melted, stretched out pieces of something that used to be on the surface, now sitting hundreds or even thousands of kilometers down. And the weird part is, we don't always know where they came from. Some might be remnants of long-vanished oceans or microcontinents that were completely consumed by subduction, while others could be pieces of early Earth crust that got recycled and trapped in the mantle. So it's not that there are hidden, intact continents just sitting under our feet, waiting to be discovered. It's that Earth has been recycling itself for so long that parts of its past are literally buried inside it, and we're only just starting to map them out using indirect methods. which makes it less like uncovering a lost world and more like realizing the planet is full of fragmented memories of its own history, scattered deep below the surface. Story 7. The weird thing about parts of the North Sea is that when geologists started mapping what's beneath it using seismic surveys, they expected to see the usual story: nice, orderly layers of sediment stacked over time, oldest at the bottom, youngest at the top, following the basic rules like the law of superposition. But in some regions, that's not what showed up at all. Instead, they found structures where layers look disrupted, folded, or even inverted in ways that don't match the clean textbook version of how sedimentary basins are supposed to form, with features cutting through older rock, strange domes, and chaotic patterns that look more like something has pushed through or rearranged the layers after they were already in place. One of the big culprits behind this is salt tectonics, where thick underground salt deposits behave more like a slow-moving fluid over geological time, rising up through overlying rock and distorting everything above them, creating domes, ridges, and warped layers that can look completely out of order. Then you add in glacial activity from past ice ages, where massive ice sheets advanced and retreated across the region, eroding, compressing, and redistributing sediments in ways that further scrambled the record. And, on top of that, faulting and tectonic movement can shift entire blocks of rock around, tilting or overturning them so that the original layering gets obscured or reversed. So while it might look like the basic rules of geology are being broken, it's more that multiple processes have acted on the same region over long periods, overprinting the original structure. It's not a clean timeline anymore. It's a heavily edited one, where the original order is still there somewhere, but buried under a lot of geological rewriting. Story 8. The Mariana Trench is one of those places that already feels extreme just based on depth alone. But what makes it really strange is that some of the conditions down there don't quite match what scientists expected, even for the deepest parts of the ocean. At first glance, it should just be a very deep, very cold, very high-pressure environment created by one tectonic plate being forced beneath another, a classic subduction zone, just taken to the extreme. And in many ways, it is. But when researchers started studying it more closely, they found pockets and zones where the chemistry, temperature, and even biological activity don't line up neatly with standard models. For example, there are areas with unusual chemical signatures, including elevated levels of certain compounds that suggest fluids are being released from deep within the subducting plate, carrying materials that have been trapped for millions of years and then injected into the surrounding environment. There are also zones where microbial life thrives in conditions that should be incredibly hostile, feeding off chemical energy rather than sunlight, which isn't unique to the trench, but takes on a different scale and intensity at those depths. And then there's the physical structure itself, which isn't just a smooth, continuous trench, but a complex landscape with faults, ridges, and variations that affect how pressure, temperature, and materials are distributed. So instead of being a simple deep ocean floor, it ends up being a dynamic system, where geology, chemistry, and biology all interact in ways that are still being mapped out. It's not that the trench breaks the rules of Earth science. It's that it pushes those rules into extremes where small differences become much more noticeable, and where processes that are subtle elsewhere become dominant forces, shaping the environment. And because it's so hard to access, every new dataset tends to add more questions along with the answers, which is why it still feels like one of the least familiar places on the planet, even though we know exactly where it is. Story 9. The origin of deep ocean methane bursts is one of those things that sounds straightforward at first, because methane is a known byproduct of biological activity and geological processes. But once you start looking at where and how some of these releases happen, the simple explanations don't always cover everything. A lot of methane in the ocean is locked away in the form of methane hydrate, sitting in cold, high-pressure environments along continental margins, basically frozen gas waiting for the right conditions to destabilize. So, one explanation is temperature change. If the ocean warms even slightly at certain depths, those hydrates can break down and release methane into the water column, sometimes in large plumes. That part is understood. But there are cases where methane eruptions seem to happen without a clear warming trigger, or in patterns that don't line up neatly with known temperature changes or pressure shifts. Some releases appear to be tied to tectonic activity, where small shifts in the seafloor crack open pathways for gas to escape, while others might be linked to changes in sediment stability, underwater landslides, or fluid movement deep below the seabed. There's also the question of how much of this methane comes from biological sources versus deeper, abiotic processes, where methane is generated through chemical reactions in the Earth's crust and mantle, which is still an area of active research. And the reason it matters is that methane is a powerful greenhouse gas, so understanding how and when it gets released from the ocean has implications for climate over long timescales. So it's not that the origin is completely unknown, it's that there isn't a single, clean mechanism that explains all of it. And in some cases, the timing and scale of these eruptions don't fully match the models we have, which makes it one of those systems where we understand the pieces, but not always how they come together in real-world conditions. Story 10. Massive underwater sinkholes sound like something out of a disaster movie, but they're actually real features, and what makes them unsettling is not that we don't understand them at all, but that they can form and collapse in ways that are hard to predict, even when we know the general mechanism. A lot of these are related to what geologists call submarine collapse structures, often linked to things like methane hydrate or buried gas pockets, where the seafloor is being supported by materials that are stable only under very specific pressure and temperature conditions. As long as those conditions hold, everything looks normal. But if something shifts, even slightly, like a change in pressure, a small temperature increase, or tectonic movement, those supports can fail, and when they do, the sediment above can suddenly collapse downward, creating large depressions or crater-like features on the seafloor. In other cases, it's more like a slow, weakening process that eventually gives way, where fluids moving beneath the seabed gradually erode or destabilize layers until they can no longer hold their structure. There are also carbonate dissolution processes, especially in areas with limestone or similar materials, where chemical interactions slowly eat away at the rock from below, eventually leading to collapse. What makes them feel unpredictable is that a lot of this happens out of sight and over long timescales, until the final failure happens relatively quickly compared to the buildup. So when these features appear, it can look sudden, even though the conditions leading to them may have been developing for years or longer. And while they don't usually pose a direct threat to people on the surface, they can impact underwater infrastructure like pipelines or cables, and in some cases, trigger localized disturbances in the water column. So it's not a completely mysterious phenomenon. But it's one of those systems where the triggers are subtle, the buildup is hidden, and the final result can look abrupt enough that it still feels unpredictable. Story 11. The Bimini Road is one of those places that keeps getting pulled into mystery territory because of how oddly structured it looks at first glance, like a paved road or a deliberately laid pathway sitting on the ocean floor. It's made up of large, flat, rectangular limestone blocks arranged in a roughly linear pattern, which is exactly the kind of geometry that makes people think this looks built, especially when you see photos from certain angles where it really does resemble something man-made. And because of that, it's been tied to all kinds of ideas, including lost civilizations and even connections to Atlantis. But when geologists look at it more closely, the explanation becomes a lot less dramatic, even if it's still interesting. The formation is made of beach rock, which forms when sand and shell fragments get cemented together along ancient shorelines, and over time, natural processes like erosion, wave action, and fracturing can break that rock into blocks that look surprisingly regular. Those fractures often follow patterns that create straight edges and right angles, which gives the illusion of deliberate construction. Then, as sea levels changed over thousands of years, what used to be a shoreline ended up underwater, leaving behind these broken slabs arranged in a way that looks intentional. So the current consensus is that it's a natural formation shaped by geological processes, rather than a constructed road. But the reason it keeps coming up is because it sits right at that boundary where natural patterns start to look artificial, and our brains are really good at seeing design even when it isn't there. So it's not a hidden ruin. It's a good example of how nature can accidentally mimic structure well enough to make people question it. Story 12. The fact that huge portions of the ocean floor are still basically unmapped sounds strange at first, because we've mapped Mars, the Moon, and even distant planets in incredible detail, so it feels like mapping our own planet should be the easy part. But the reality is that the ocean is just a much harder environment to work in. Water blocks most forms of direct observation, especially light, so satellites can't see the seafloor the way they can map land. And while we can use sonar to map underwater terrain, that requires ships physically traveling over the area, sending sound waves down and measuring how they bounce back, which is slow, expensive, and limited by how much area a vessel can cover. The Pacific Ocean alone is so vast that even with modern technology, mapping it at high resolution would take an enormous amount of time and resources. And a lot of regions are remote, deep, and not considered a priority compared to coastal areas, shipping routes, or resource zones. There are global maps of the seafloor created using satellite data that measure tiny changes in sea surface height caused by gravitational differences, which gives a rough outline of underwater features, but those maps are much lower resolution than direct sonar surveys. So it's not that we have no idea what's down there. It's that much of it is only known in broad strokes, like knowing the shape of a mountain range without seeing the individual peaks and valleys. And the deeper you go, the harder it gets, because pressure, darkness, and distance make detailed exploration increasingly difficult. So the reason entire underwater landscapes remain unmapped isn't because they're being hidden. It's because mapping them in detail is one of the most logistically challenging things we can do on this planet. And we're still in the process of filling in the gaps. Story 13. The fairy circles are one of those things that look so perfectly arranged that your first instinct is that something must be organizing them. Because they aren't random at all, they form these evenly spaced, almost geometric patterns across huge stretches of desert, especially in places like Namib Desert. Each circle is a patch of bare ground surrounded by grass, and when you zoom out, they create this repeating pattern that looks more like something designed than something natural. Which is why for a long time people threw around all kinds of explanations, from underground gases to insects to more speculative ideas. But when scientists started studying them closely, the picture that emerged wasn't a single cause, but a kind of self-organizing system driven by competition for resources, especially water. In extremely dry environments, plants are constantly competing for limited moisture. And what seems to happen is that vegetation naturally spaces itself out in a way that maximizes access to water, creating these gaps where nothing can grow because surrounding plants are effectively drawing resources away. Over time, that competition stabilizes into a pattern, where each patch maintains a kind of personal space, and because the conditions are consistent across the landscape, the pattern repeats in a way that looks structured. There's also evidence that in some regions, things like termites may play a role in shaping or maintaining the circles, which adds another layer to it. So instead of a single hidden cause, it's more like a feedback system between plants, soil, and water, where simple interactions at a small scale produce these large, organized patterns. And that's what makes it interesting. Not that it's unexplained, but that something as simple as plants competing for water can create patterns that look so precise they almost feel intentional. Story 14. Singing sand dunes are one of those things that sound like pure folklore until you actually hear them, because under the right conditions, entire dunes can produce these deep, resonant, almost musical tones that carry for kilometers. And it really does sound like the ground itself is making noise. They've been reported in deserts all over the world, including places like the Sahara Desert. And the sound isn't random either. It can be a low hum, a booming vibration, sometimes even something that resembles a sustained note, which is what makes it feel so unnatural. For a long time, people threw out all kinds of explanations, from wind whistling through grains to underground echoes, but those didn't fully explain why the sound can be so loud, so consistent, and so tonal. What researchers have found is that the sound is tied to avalanches of sand moving down the face of a dune. But not just any sand will do it. The grains have to be very uniform in size and shape, dry and smooth, and when they start moving together in a certain way, they can synchronize their motion. That synchronization is the key. Instead of each grain moving randomly, large numbers of them move in unison, creating vibrations that amplify each other and produce a coherent sound wave, almost like a natural instrument. But even with that explanation, there are still gaps. Not all dunes with similar sand will sing, and the exact conditions needed to trigger and sustain the sound aren't fully understood, which is why it still feels a bit mysterious. So it's not that there's no cause, it's that the system is sensitive, and we don't completely understand why it works in some places and not others, which leaves it sitting in that space where it's explained in principle, but still not entirely predictable in practice. Story 15. The idea of rivers flowing uphill sounds like it should break the laws of physics, but what's actually happening in most of these cases is that our perception is getting tricked by the landscape in a way that's surprisingly convincing. There are places often called gravity hills or magnetic hills, where water, cars in neutral, or even rolling objects appear to move against gravity, and it really does look like something impossible is happening if you're standing there without context. But what's going on is a visual illusion. The surrounding terrain, the slope of the land, the horizon line, and the lack of clear reference points combine to make a slight downhill gradient look like an uphill one. So when water flows naturally downhill, your brain interprets it as moving upward. It's basically the same kind of misperception you get in certain optical illusions, just scaled up to a landscape level. That said, there are also more subtle cases where rivers seem to behave oddly, like flowing in unexpected directions, or changing course in ways that look unnatural. But those are usually tied to geological factors like tectonic shifts, erosion patterns, or ancient riverbeds being altered over time. So the against gravity idea isn't literally true. Water is still following gravity exactly as it should, but the way we interpret the environment can be misleading enough that it feels like the rules are being broken even when they're not. And that's what makes it interesting. Not that physics is failing, but that our perception of it can be fooled so easily when the visual cues we rely on aren't what we think they are. Story 16. The whole lake suddenly turns bright pink thing, looks like something chemical got dumped into the water, or something seriously wrong happened, but most of the time it's actually a natural shift that just becomes visible all at once when the conditions line up. Places like Lake Hillier or Lake Retba are famous for it, and the color isn't coming from dye or pollution in the usual sense. It's coming from microorganisms, mainly algae and bacteria that produce pigments. In particular, organisms like Dunaliella salina thrive in very salty environments, and when conditions are right, high salinity, strong sunlight, and limited competition from other life, they multiply rapidly and produce compounds like beta-carotene, which gives the water that intense, pink or reddish color. What makes it feel sudden is that those conditions can shift fairly quickly. A dry period can increase salinity, temperature changes can affect growth rates, and once the balance tips in favor of those organisms, the population can bloom fast enough that the color change looks almost immediate. Then when conditions shift back, like after heavy rain dilutes the lake, the color can fade again. So it's not that the lake is permanently pink or that something unusual just appeared out of nowhere. It's more like a biological response that becomes visible when the environment crosses a certain threshold. And like a lot of these examples, it's not mysterious in the sense of being unexplained, but it still feels strange because it's such a dramatic, almost unnatural-looking change caused by something as simple as microbes responding to their environment. Story 17. Perfectly circular depressions in the landscape are one of those things that immediately make people think something unusual must have happened, because nature tends to produce messy, irregular shapes, so when you see a near-perfect circle carved into the ground, it feels like it should have a clean, single explanation behind it. And sometimes it does. In certain cases, these formations are tied to known processes like sinkholes, impact craters, or volcanic features, each of which can produce roughly circular shapes under the right conditions. But the reason this topic keeps coming up is that not all of these depressions fit neatly into those categories. Some appear in clusters, some form in environments where the usual explanations don't fully apply, and others show up with a level of symmetry that's hard to attribute to a single obvious cause. One example people often point to is Carolina Bays, which are thousands of similarly shaped features spread across a large region, all aligned in roughly the same direction, which has led to a long-running debate about how they formed. Proposed explanations range from wind and water shaping loose sediments over time, to melting permafrost, to more exotic ideas that don't hold much support, but none of them fully explains every detail. In other parts of the world, circular depressions can form through underground collapse, gas release, or fluid movement that weakens the ground from below, eventually causing the surface to give way in a way that naturally creates a rounded shape. What makes them feel mysterious isn't that there's no explanation at all, but that different processes can produce very similar results. And in some cases, we don't have enough data to confidently say which one is responsible. So instead of one hidden cause, it's more like a category of features where multiple mechanisms overlap, and the challenge is figuring out which one applies in each specific case, which leaves some of them sitting in that uncomfortable space between explained in general and not fully understood in detail. Story 18. The weird thing about certain landscapes is how intentional they look, like someone planned them out with straight edges, repeating patterns, or clean geometry, even though they're entirely natural. And once you notice it, it's hard to unsee. You get places where cliffs look like they were cut with tools, valleys that look too symmetrical, rock formations that almost resemble walls, roads, or terraces, and your brain immediately jumps to, "This looks designed," because we're wired to recognize patterns in structure. But what's actually happening is that natural processes can be way more organized than we expect. Things like erosion, fracturing, and sediment deposition don't always act randomly. They often follow underlying structures in the rock, like faults, joints, or layers that guide how material breaks apart, which can create straight lines, sharp edges, and repeating forms. A good example is Giant's Causeway, where cooling lava contracts and fractures into near-perfect hexagonal columns, which looks so artificial that people originally thought it had to be constructed. Then you've got wind and water erosion, which can carve landscapes over long periods in ways that amplify symmetry, especially when conditions stay consistent, creating features that look almost engineered. Even things like river systems can develop patterns that resemble planned networks, just because they're following the path of least resistance over time. So what feels artificial is really just natural processes acting under constraints that produce order instead of chaos. And the reason it feels uncanny is because we tend to associate clean patterns with intelligence. So when nature produces them on its own, it creates that disconnect between what we expect and what we're actually seeing. It's not that the landscape was carved with intent, it's that nature doesn't have to be random to be natural. Story 19. The idea of supervolcano sitting there, fully capable of reshaping the planet, but just not erupting, is one of those things that sounds more mysterious than it actually is at first, until you realize how much uncertainty there still is in how these systems behave. Places like Yellowstone caldera are often brought up because they've had massive eruptions in the distant past, the kind that leave huge calderas behind. And when people look at that history, the question becomes, why hasn't it happened again if the system is still there? The assumption used to be that these systems build up pressure over time like a ticking clock, and eventually they have to release it in a catastrophic eruption. But newer research suggests it doesn't work that way. Instead of a single, large, molten chamber just waiting to blow, what's actually down there is more like a complex mix of partially molten rock, solid material, and fluids, where melt is distributed and often not in a state that can erupt easily. So even if there's heat and magma present, it doesn't automatically mean an eruption is imminent. The system can sit in that state for extremely long periods, with magma cooling, crystallizing, moving, and being reabsorbed into the surrounding rock without ever reaching the conditions needed for a massive eruption. There are also feedback mechanisms, like the release of gases or small-scale volcanic activity, that can relieve pressure gradually instead of allowing it to build up to a catastrophic level. So the reason they haven't erupted isn't really unknown in the sense of being mysterious or hidden. It's that the original idea of them as ticking time bombs was too simplistic. They're more like dynamic systems that can remain stable for hundreds of thousands or even millions of years, with the right conditions for a super eruption being much rarer than people once thought, which makes them less immediately threatening, but still unsettling in a different way, because when those rare conditions do line up, the scale of what happens is on a completely different level. Story 20. The unsettling thing about massive volcanic eruptions isn't just the scale, it's that even with all the monitoring we have now, the exact trigger that pushes a system from stable to catastrophic isn't always clear or predictable. We understand the basics behind a volcanic eruption. Magma accumulates, gases build pressure, and eventually something gives, but that something is where it gets messy, because not every magma system behaves the same way, and not every buildup ends in an eruption. In many cases, volcanoes show warning signs like increased seismic activity, ground deformation, or gas emissions, which gives scientists a window into what's happening below. But even then, those signals don't always lead to an eruption, and sometimes, large eruptions seem to escalate faster than expected. One of the key unknowns is how pressure actually gets released or contained within complex underground systems, because magma chambers aren't just simple cavities, they're networks of partially molten rock, cracks, and pathways that can open or seal over time. A small change, like new magma injection, shifting tectonic stress, or even the movement of fluids, can tip the balance. But figuring out which of those factors will actually trigger an eruption in a given situation is extremely difficult. There's also evidence that some systems can sit near a critical threshold for long periods, where they're technically unstable but not yet erupting, until a relatively minor disturbance pushes them past the tipping point. So it's not that eruptions come out of nowhere, but the final trigger can be subtle enough that it's hard to identify in advance, especially when everything is happening kilometers below the surface. And that's what makes it feel unpredictable. We can see the buildup, we just don't always know what the final push will be. Story 21. The idea that certain ancient eruptions came close to wiping out most life on Earth isn't speculation. There are real events in the geological record where something went catastrophically wrong on a planetary scale. But what still isn't fully nailed down is exactly what triggered them, and why they got so extreme. One of the biggest examples is the Permian-Triassic extinction event, where around 90% of marine species and a huge percentage of land life disappeared, and the leading suspect is massive volcanic activity known as the Siberian Traps. But this wasn't a single eruption like a volcano blowing its top. It was something much larger and slower, enormous volumes of lava erupting over hundreds of thousands of years, releasing massive amounts of gases like carbon dioxide and sulfur dioxide into the atmosphere. That alone could have driven extreme climate change, ocean acidification, and oxygen loss, all of which are consistent with what we see in the fossil record. But even that might not be the whole story. There's evidence suggesting feedback loops, like warming oceans releasing methane, which would amplify the greenhouse effect even further, or chemical reactions between magma and underground deposits releasing additional toxic gases. And then there's the question of timing. Why did this system suddenly ramp up into such an intense, prolonged event, instead of staying at a lower level of activity like many other volcanic regions? That part isn't fully understood. So while we can connect these extinction events to large-scale volcanism with a high degree of confidence, the exact chain of triggers and amplifying factors is still being pieced together. And that's what makes it unsettling. Not that we don't know what happened in general, but that the difference between a normal volcanic system and one that nearly resets life on Earth might come down to a combination of factors we don't completely understand even now. Story 22. The strange thing about volcanoes is that dormant doesn't mean dead. It just means inactive for now, and in some cases that now can stretch for tens of thousands of years, which makes it feel like they've basically shut off, until suddenly they don't. A volcano isn't just a simple pipe connected to a constant source of magma. It's part of a much more complex system where melt is generated, stored, cooled, and sometimes reabsorbed deep underground. In many cases, magma doesn't just sit there waiting to erupt. It can cool and crystallize over time, becoming more solid and stable, which effectively locks the system and prevents movement toward the surface. Then you add pressure dynamics. Gases dissolved in magma are what drive explosive eruptions. But if those gases slowly escape over time, or if the surrounding rock can absorb or redistribute pressure, the system can remain stable for extremely long periods without building toward an eruption. There's also the role of tectonics. If the stress conditions in the crust aren't right, pathways for magma to rise may never fully open. So even if there's melt deeper down, it doesn't have a clear route to the surface. And what makes it unpredictable is that all of this can change. New magma can be injected from below, reheating and remobilizing older material. Tectonic stress can shift, or fractures can open, and a system that's been quiet for thousands of years can suddenly become active again. So the long dormancy isn't mysterious in the sense of being unexplained. It's more that these systems can sit in a kind of stable equilibrium for incredibly long times until something disrupts that balance. And when that happens, it can look sudden, even though the conditions that allowed it were building quietly far below the surface the entire time. Story 23. The strange part about magma movement is that we've built models that work really well in simple cases. But when you look at what's actually happening beneath real volcanoes, it often doesn't follow those clean patterns at all. In theory, magma should rise because it's less dense than the surrounding rock, moving upward through fractures or pooling in chambers before eventually erupting. And that basic idea is solid. But when scientists track magma using seismic signals, ground deformation, and gas emissions, the behavior can look erratic. You get magma moving sideways instead of up, stalling for long periods, splitting into multiple paths, or even reversing direction, which isn't what simple buoyancy-driven models would predict. Some systems show pulses of movement that start and stop without leading to eruptions, while others build slowly and then suddenly accelerate in ways that don't match earlier patterns. Part of the problem is that magma doesn't move through empty space. It's interacting with solid rock that can crack, deform, or seal itself again, and those interactions can change the available pathways in real time, meaning the route magma takes isn't fixed. Then you have variations in composition, temperature, and gas content, all of which affect how fluid or viscous the magma is, which in turn changes how it behaves under pressure. And all of this is happening kilometers underground, where we can't observe it directly, so we're reconstructing the process from indirect signals that don't always tell a complete story. So it's not that there's no explanation, it's that the system is so complex, with so many interacting variables, that no single model captures all of it consistently, which leaves us with a situation where we understand the principles, but not always the exact behavior in any given case, especially when things start deviating from the expected path. Story 24, the Rechat structure, often called the Eye of the Sahara, is one of those formations that looks so perfectly circular and massive that the first instinct is to assume it must be an impact crater, because what else makes something that symmetrical on that scale? From space, it really does look like a target, concentric rings stretching across tens of kilometers, which is why for a long time people assumed it had to be the result of a meteor strike. But when geologists studied it up close, that explanation didn't hold up. There's no evidence of the kind of shock features you'd expect from an impact, like shocked quartz or melted rock. And the structure itself doesn't match the typical profile of a crater once you look beyond the surface symmetry. So, the current understanding is that it's actually a deeply eroded dome, where layers of rock were pushed upward over time and then gradually worn down by erosion, exposing those layers in circular patterns. Different rock types erode at different rates, so what you end up seeing are these rings where harder layers stand out and softer ones get worn away, creating that eye-like appearance, which makes it less of a sudden event and more of a slow process playing out over millions of years. But even with that explanation, there are still details that aren't completely settled, like exactly what caused the original uplift and why it formed such a symmetrical structure in the first place. So it's not a mystery in the sense of being totally unexplained, it's more that the broad mechanism is understood, while the finer details are still being worked out. And that's kind of what makes it interesting, because it looks like something dramatic and instantaneous, but it's really the result of long-term processes that just happen to produce a shape that feels almost too perfect to be natural. Story 25. The weird thing about perfectly circular formations is how quickly our brains jump to meteor impact, because circles that are clean and large just don't feel like something nature produces on its own, especially when they show up in isolation in the landscape. And, to be fair, a lot of real impact craters do look exactly like that, which is why the assumption stuck for so long. But the more geologists studied these features, the more they realized that circular shapes can come from a bunch of completely different processes that have nothing to do with something hitting Earth from space. Some are volcanic in origin, where underground pressure pushes rock upward into a dome, and then erosion strips it down over time, leaving behind ring-like structures, similar to what you see in places like the Richat structure. Others form through collapse, where underground cavities or weakened rock give way, and the surface sinks inward, naturally creating a rounded depression. There are also salt domes, where buried salt slowly rises through overlying rock and distorts the layers above it into circular patterns, and even chemical processes where different minerals erode at different rates, carving out ringed shapes over long periods. What makes it tricky is that, from above, a lot of these can look nearly identical to impact craters. So scientists have to look for very specific evidence, like shocked minerals or melt signatures, to confirm whether an actual impact happened. And in many cases, that evidence just isn't there. So what looks like something dramatic and sudden can actually be the result of slow, internal processes shaping the Earth over millions of years. And that's what makes it interesting. Not that the circles are unexplained, but that very different mechanisms can produce the same kind of shape, which makes first impressions pretty unreliable when it comes to geology. Story 26. The strange thing about some giant rock formations is how deliberate they look, like they've been carved, stacked, or aligned with intention, even though they're entirely natural. And once you see that symmetry, it's hard not to feel like something about it doesn't quite add up. You get massive pillars, flat faces, near-perfect columns, or repeating geometric patterns that look way too clean to be the result of random processes, and your brain immediately tries to map that onto something familiar: architecture, construction, design, because that's how we're wired to interpret symmetry. But what's actually happening is that geology isn't random at all. Rock breaks along weaknesses, like joints, faults, or crystal boundaries, and when those weaknesses are evenly spaced or follow consistent patterns, the result can look incredibly structured. A classic example is Giant's Causeway, where cooling lava contracts and fractures into hexagonal columns so regular that they look like they were laid out on purpose. And it's not just lava. Sedimentary layers can erode in ways that create flat plains and sharp edges. Tectonic stress can fracture rock into repeating blocks, and long-term weathering can refine those shapes over millions of years, stripping away irregularities and leaving behind forms that look almost engineered. What makes it feel unnatural isn't the process, it's the scale and precision, because we tend to associate that kind of order with intelligence, not with slow physical forces acting over vast periods of time. So it's not that these formations defy natural explanation, it's that natural processes, given enough time and the right conditions, can produce results that look far more intentional than we expect, and that disconnect between expectation and reality is what makes them feel so mysterious. Story 27. The strange thing about stone pillars and columns with near-perfect geometry is that they look so clean and repetitive that your brain immediately reads them as artificial, like something stacked or carved with intention, even though they're entirely the result of natural processes playing out under very specific conditions. One of the best-known examples is Giant's Causeway, where thousands of interlocking hexagonal columns rise out of the ground like a tiled floor turned vertical. And at first glance, it genuinely looks engineered, because the shapes are so consistent and tightly packed. But what's actually happening is surprisingly mechanical. When lava cools, it contracts, and as it contracts, it cracks, and those cracks tend to form in patterns that distribute stress evenly, which often results in hexagonal shapes, because hexagons are one of the most efficient ways to fill space without gaps. So instead of random fractures, you get a repeating pattern emerging naturally as the material cools and shrinks. And it's not just one place. Similar formations show up in different parts of the world, wherever the conditions are right. Same type of lava, similar cooling rates, similar environmental constraints, which reinforces the idea that this isn't a one-off anomaly, but a predictable outcome of the physics involved. What makes it feel uncanny is the precision. We tend to associate straight lines, sharp angles, and repeating geometry with design. So when nature produces those same features, it creates that disconnect where it looks intentional even when it isn't. So it's not that these pillars are unexplained, it's that the explanation involves simple physical rules applied over time, producing results that look far more deliberate than we expect from something we think of as natural. Story 28. Massive ring-shaped landforms are one of those features that instantly trigger the "this has to be from an impact" reaction, because circles that large and clean don't feel like something that should just happen randomly, especially when they show up in isolation and dominate the surrounding landscape. And sometimes that instinct is right. Some of these really are impact craters. But the reason this topic stays messy is that a lot of ring-shaped structures don't have the telltale signs you'd expect from an impact. No shocked minerals, no melt layers, no clear ejecta patterns, which means something else had to create them. A good example people point to is the Rechat structure, which looks almost like a giant target from above, but isn't an impact at all and instead seems to be the result of uplift and erosion exposing circular layers over time. Then you've got other possibilities, like ancient volcanic systems, where collapsed magma chambers can leave behind ring-like features, or salt domes where underground salt slowly pushes upward and warps the surrounding rock into circular patterns. There are also cases where tectonic stress fractures rock in ways that create curved or ringed structures, especially when combined with erosion that emphasizes those shapes over millions of years. What makes it feel unresolved is that different processes can produce very similar results. And in some cases, the evidence isn't clear enough to definitively say which one was responsible. So instead of one explanation that fits everything, you end up with a category of formations where each case has to be studied individually. And some still don't have a fully agreed upon origin, which leaves them sitting in that weird space where they're not completely unexplained, but not fully settled either, especially when the shape itself is so striking that it feels like it should have a simple answer. Story 29. The weird thing about earthquake lights is that they sound like pure folklore at first, like something people imagined in the chaos of an earthquake. But there are enough consistent reports, and even some photos and videos now, that scientists have had to take them seriously. People describe flashes in the sky, glowing orbs, or sheets of light that appear before or during seismic activity, sometimes hovering near the ground, sometimes lighting up the horizon. And the descriptions are similar enough across different regions and time periods that it's hard to just dismiss them as coincidence. For a long time, there wasn't a solid explanation. Earthquakes are about rock breaking and shifting underground, so visible light didn't really fit into the picture. But more recent ideas suggest it could be related to electrical charges building up in certain types of rock under stress, especially when tectonic forces are compressing or fracturing the crust. As rocks deform, they can generate electrical currents, and under the right conditions, those charges might travel to the surface and interact with the atmosphere, producing visible light. That's one of the leading explanations, but it doesn't cover every report. Not all earthquakes produce lights, and not all locations seem equally likely to show them, which suggests the conditions have to be very specific, possibly involving particular rock compositions or fault structures. So it's not completely unexplained anymore, but it's still not fully predictable either. And that's what keeps it in that gray area. We have a plausible mechanism, but not a complete understanding of when or why it actually happens. Story 30. The strange thing about earthquakes is that we tend to associate them strictly with visible fault lines, like the boundaries where tectonic plates meet, so when one happens far away from those zones, it feels like something is off or missing from the explanation. But the reality is that earthquakes don't actually require a clearly mapped surface-level fault to occur. They just require stress in the crust and a weakness somewhere for that stress to be released. And that's where things get interesting. The Earth's crust isn't a perfectly uniform shell, it's full of old buried faults, fractures, and zones of weakness that may not be visible at the surface or even well understood, especially in regions that haven't been tectonically active for a long time. So in what are called intraplate earthquakes, stress can build up over long periods due to forces transmitted across entire tectonic plates, and eventually that stress finds one of those hidden weak points and releases suddenly. A well-known example is the New Madrid seismic zone, which has produced significant earthquakes despite being far from a major plate boundary. In some cases, human activity can also play a role, like fluid injection, mining, or reservoir-induced stress changes, which can alter pressure conditions underground and trigger seismic events in places that otherwise seem stable. What makes it feel mysterious is that these areas don't show the same clear warning signs or long histories of activity as major fault zones. So when an earthquake happens there, it seems to come out of nowhere. But it's not random. It's stress finding a path we didn't fully map. And that's what makes it unsettling. Not that the rules are being broken, but that the map we're using isn't as complete as we think. Story 31. The unsettling thing about sudden land collapses is how they can look completely random from the surface, like solid ground just gives way without warning, even though the processes behind them are usually building quietly for a long time out of sight. Most of these events fall under things like sinkholes or subsidence, where the ground is being weakened from below, often in areas with soluble rock like limestone, where water slowly dissolves the material over time, creating underground voids that you'd never know were there until the roof finally fails. That's the basic idea behind sinkhole formation, and in many cases, there actually are warning signs. Things like small cracks, subtle settling, or changes in drainage. But they can be easy to miss or happen too gradually to notice. What makes it feel unpredictable is that the final collapse can happen very quickly once the structure underneath reaches a tipping point, so something that's been weakening for years or decades can fail in a matter of minutes. There are also other triggers that complicate things, like heavy rainfall, groundwater changes, or human activity such as construction or water extraction, all of which can shift the balance enough to cause a sudden failure. And in some cases, it's not just dissolution, but buried cavities, old mine workings, or even gas movement that destabilizes the ground from below. So it's not that these collapses have no cause. It's that the cause is hidden, gradual, and often only visible in hindsight, which is why they feel so sudden and hard to predict when they finally happen. Story 32. The strange thing about these underground energy releases is that they don't show up as clean textbook earthquakes, but instruments still pick up signals that something just happened deep below the surface, even when there's no obvious fault slip or eruption to point to. Seismometers are incredibly sensitive, and they don't just detect classic quakes, they also pick up all kinds of subtle events, from slow slips to fluid movement, and sometimes those signals don't match the patterns scientists expect from a normal earthquake. One example is what are called low-frequency or slow earthquakes, where energy is released over longer periods instead of a sharp jolt, producing signals that look very different from typical seismic activity, and in some cases, barely register as shaking at the surface at all. Then there are deep tremors linked to fluids moving through rock, like water or molten material shifting under pressure, which can generate energy releases without the kind of fracturing we usually associate with earthquakes. You also get events tied to things like magma movement, gas release, or even stress redistribution in the crust, where energy is released as the system adjusts, but not in a way that produces a classic quake signature. What makes it feel mysterious is that these signals can appear in places or at depths where the standard models don't fully explain what's happening, or they show patterns that don't fit neatly into known categories. So it's not that scientists have no idea what they are. It's that these events sit at the edges of what we understand, where multiple processes can produce similar signals, and the data we get isn't always detailed enough to clearly separate them, which leaves some of these energy releases in that gray area, not unexplained, but not fully pinned down either, especially when they don't behave the way we expect. Story 33. The Snowball Earth idea is one of those concepts that sounds almost impossible at first, because the thought of the entire planet, oceans, continents, everything, locked under ice for millions of years feels like it should leave obvious, simple evidence behind. But the deeper you look, the more complicated the cause becomes. There's strong geological evidence that something like this did happen, based on glacial deposits found in places that were once near the equator, which means ice wasn't just at the poles, it was widespread. The leading explanation is a kind of runaway feedback loop. As ice spreads, it reflects more sunlight back into space, which cools the planet further, which allows even more ice to form, and once that process passes a certain threshold, it can accelerate into near-global glaciation. But that still leaves the question of what started it. One idea is that changes in atmospheric carbon dioxide levels played a major role, possibly due to increased weathering of rocks pulling CO2 out of the atmosphere, reducing the greenhouse effect enough to trigger the initial cooling. Another possibility involves the arrangement of continents at the time, which may have enhanced weathering or disrupted ocean circulation in ways that made the climate more unstable. There are also suggestions that volcanic activity, solar output variations, or even biological changes could have contributed in ways we don't fully understand. And that's where it gets uncertain, because while the feedback mechanism explains how the planet could stay frozen once it started, the exact trigger or combination of triggers that pushed Earth into that state in the first place isn't fully agreed upon. So it's not a mystery in the sense that we don't know what happened, it's that we're still piecing together why it started when it did, and why it tipped so dramatically instead of stabilizing at a milder level. Story 34. The strange thing about ice ages is that we actually understand a big part of the mechanism behind them, but they still don't behave as cleanly or predictably as you'd expect, for something that affects the entire planet. At the core of it are cycles known as Milankovitch cycles, which change how sunlight is distributed across Earth over tens of thousands of years, and these shifts can nudge the climate toward cooling or warming. On paper, that sounds like a nice, predictable system. Orbital change happens to climate responds to ice sheets grow or shrink. But when scientists look at the actual timing of ice ages, the pattern isn't that neat. Some glacial periods last longer than expected. Others end more abruptly, and the transitions between ice ages and warmer periods don't always line up perfectly with the orbital cycles alone. That's because those cycles are more like a trigger than a full explanation. What really controls the system are feedback loops. Ice reflects sunlight, so more ice means more cooling, while greenhouse gases like CO2 trap heat, so changes in atmospheric composition can amplify or dampen those orbital effects. Then you add in ocean circulation, which can redistribute heat globally, and even small shifts in currents can push the climate in one direction or another. The problem is that all of these factors interact, so instead of a simple cause and effect, you get a system where multiple variables are constantly influencing each other, sometimes reinforcing, sometimes canceling out. Which is why ice ages don't start and end like clockwork. We know the main drivers, we just can't always predict exactly how they'll combine in real time, or why the system tips one way at a particular moment, instead of staying stable. Story 35. The unsettling thing about ancient climate evidence is that sometimes it shows conditions that don't seem to fit the rules we think we understand, like warm tropical environments existing where it should have been cold, or signs of glaciation showing up near what used to be the equator. And it forces you to question how stable Earth's climate system really is. There are cases where fossils of lush vegetation and warm water organisms have been found in regions that, based on their position and expected climate, shouldn't have supported that kind of life, and others where clear glacial deposits appear in places that were once close to the equator, which is one of the key pieces of evidence behind events like global-scale glaciations. At first, these kinds of findings looked contradictory. Warm climates where it should be cold, ice where it should be warm. But part of the explanation comes from the fact that continents haven't stayed in the same place over time, and plate tectonics has shifted land masses across different latitudes, meaning a place that is cold today might have once been near the equator, or vice versa. That helps resolve some of the contradictions, but not all of them, because even after accounting for continental movement, there are still periods where global conditions seem extreme in ways that are hard to reproduce with current climate models, like very high temperatures during times when atmospheric CO2 levels don't fully explain the warmth, or rapid shifts that seem too fast for the known drivers. So, it's not that the evidence is wrong, it's that the system is more sensitive and complex than the simplified models we often use. And that's what makes it interesting. Not that Earth broke its own rules, but that the rules might have more variables, thresholds, and feedback than we fully understand, especially when you stretch them across hundreds of millions of years. Story 36. The strange thing about sudden warming events in the geological record is how abrupt they look when you compress millions of years into a thin layer of rock, because you go from relatively stable conditions to a sharp spike in temperature signals, almost like the climate just flipped a switch. One of the best-known examples is the Paleocene-Eocene thermal maximum, where temperatures rose significantly over a geologically short period, and the evidence shows up in things like carbon isotopes, fossil changes, and shifts in ocean chemistry. And the leading explanation is a massive release of carbon into the atmosphere, which amplified the greenhouse effect, but the exact source of that carbon is still debated. Some ideas point to methane hydrates destabilizing on the seafloor, others to volcanic activity releasing large amounts of CO2, or even feedback loops where initial warming triggered additional releases from natural reservoirs. What makes it complicated is that these processes don't operate in isolation. You can have a small trigger that sets off a cascade, where warming causes more greenhouse gases to be released, which causes more warming, and so on, creating a rapid shift that looks sudden in the record. But even with those mechanisms, the speed and scale of some of these events are still difficult to fully reproduce in models, especially when trying to match all the evidence at once. So it's not that we don't know what happened in general terms. It's that the exact sequence of triggers and feedback, what started it, what amplified it, and why it stopped, isn't fully pinned down. And that's what makes these events feel a bit unsettling, because they show that Earth's climate system can change very quickly under the right conditions, even if those conditions aren't completely understood. Story 37. The weird thing about a lot of so-called impact craters is that once you start looking at them closely, some of them don't actually have the evidence you'd expect from something slamming into Earth at high speed, even though from above they look exactly like they should. A real impact site usually leaves behind very specific signatures, like shocked minerals, melt layers, or patterns of debris thrown outward. And when those aren't there, it raises the question of whether the crater actually came from space at all. In some cases, features that look like impact craters turn out to be volcanic in origin, like collapsed magma chambers or explosive eruptions that create circular depressions, while in others, they're linked to underground collapse, where cavities form and the surface drops in on itself. There are also structures shaped by things like salt movement or erosion, where layers get warped and worn down over time into ring-like forms that mimic the shape of a crater. A well-known example people often rethink is Richat structure, which looks almost like a giant impact target but doesn't show the key evidence needed to confirm that origin. What makes this tricky is that from a distance, these different processes can produce nearly identical shapes, so you can't rely on appearance alone to figure out what happened. And in some cases, the evidence is incomplete or has been altered over time, which makes it harder to reach a clear conclusion. So instead of every circular depression being the result of an impact, it turns out that nature has multiple ways of creating similar-looking features, and figuring out which one applies in each case can still be an open question. Story 38. The strange thing about asteroid impacts is that we know, statistically, they must have happened far more often than the geological record shows, because based on how many objects are in space and how frequently impacts occur on bodies like the Moon, Earth should be covered in far more craters than we actually see. And yet, a lot of that evidence just isn't there, or at least, not in any obvious way. We have confirmed sites like the Chicxulub crater, which clearly show what a massive impact looks like in the rock record. But when you compare Earth to the Moon, which preserves its craters almost perfectly, there's a huge discrepancy. Earth looks almost wiped clean by comparison. The main reason is that Earth is geologically active in a way the Moon isn't. Processes like plate tectonics constantly reshape the surface, subducting oceanic crust back into the mantle, uplifting and eroding continents, and effectively recycling large portions of the planet over time. Then you add erosion from wind, water, and ice, which gradually wears down surface features, and sedimentation, which can bury craters under layers of new material, hiding them from view. So, impacts that happened hundreds of millions or billions of years ago can be completely erased or obscured. But even with that explanation, there are still gaps. Some impacts we expect to find evidence for based on models or indirect signals don't have clearly identified craters, or the remnants are so altered that they're hard to confirm. So it's not that the impacts didn't happen, it's that Earth is really good at covering its tracks. And that leaves us with a record that's incomplete, where some of the biggest events in the planet's history may have left only faint or indirect traces,